Hello everyone, welcome to lecture 7. And in this lecture we're going to start chapter 3, which is on functions. And in particular, I want to first discuss the first section, which is sort of the definition of what a function is and function notation. So some of the basic ideas of functions. It's on functions and function notation. Okay, so before we start talking about functions, let's talk about a similar idea, which is called a relation. So let's start with a set of ordered pairs. So it's a set, right? So I have a curly bracket, and then in that set I have ordered pairs. I think of them as x, comma, y values. So let's say this is my set. So this is called a relation. The set of the first components of the ordered pairs is called the domain. So in this case, right, think of the first value in each ordered pair, which is typically we call it the x value, but it doesn't have to be x, but you can think of it as the x value. So the domain is going to be the set, spell this correctly. The domain is going to be the set 1, 2, 4, 7, and 9. Again, right, think of it as all the x values, right? So I just picked off, from the relation, I picked off all of the x values. That's my domain. And then the set of the second components is called the range. So in this case, the range would be the set -2, -4, 0, 4, and 1. So again, how did I get those values? I'm just picking off the second components, which of the ordered pairs, which you can think of as like the y values. So -2, -4, 0, 4, and 1. Okay, so let me further explain this. So each value in the domain is known as the input value or independent variable. And each value in the range is known as the output value or dependent variable. So the output value or dependent, also called a dependent variable. So again, typically the input values are labeled as X, right? So input is usually labeled as X. And the output values that are in the range as a group are usually labeled as Y. So output values is usually labeled as Y. Okay, so what is a function? Remember, ultimately we want to talk about functions, and we're just right now defining what a relation is. A function is basically a special relation. It's a special type of relation. So a function usually we denote it by some letter. Typically people use F, but you could use other letters as well. So function F is a relation that assigns a single element in the range to each element in the domain. So that assigns a single element in the range to each element in the domain. So the way to think about that is no X values are repeated. So I'll say no X values are repeated. Or you could also think of it, for each input, there is exactly one output. So for each input, there is exactly one output. So one simple example would be the following, right? Let's say I have a set of ordered pairs. I don't know, let's say 1, 4, 2, 5, 1, 3, 3, negative 5. I'll do one more, 4, 0. Okay, so this is a relation, right? This is a relation because any set of ordered pairs is a relation. But this is not a function. Why? Because in order for it to be a function, remember, for each input, there can only be one corresponding output. So for each X, there can only be one Y. And notice here that if any X value repeats, that means it can't be a function. So in this case, the 1, which is the input, corresponds to 4. And here, it also corresponds to 3. But we can't have two outputs for one input in order for it to be a function. So this is a relation, but not a function. Whereas if I have something like this, let's say negative 2, 5, negative 1, 0, 0, 2, 1, negative 3, and then 2, 10. Let's say that's my, so this is a relation, right? Because any set of ordered pairs is going to be a relation, but it's also a function because for each input, there's exactly one output, right? So a quick way to check that is the x values don't repeat. So if the x values don't repeat, it is a function. So relation, and I'll say, and also a function. What about this? What if I have negative 2, 3, negative 1, 3, 0, 3, 1, 3, 2, 3. Is that a function? Yes. So the output, it's fine if the output repeats, right? It's the input that can't repeat. So for each input, so in this case, the 2, the negative 1, there's only one corresponding output, and it happens to be the same, but that's okay. So this is also a function, right? So the only thing you have to check is, in order for it to be a function, is the input can't repeat, the x can't repeat. So it's a relation, of course, and it's also a function. Okay, let's talk a little bit about function notation. So the notation y equals f of x defines a function named f. Now, the way that you read this is you can read it as y is a function of x. So I'll say I'll write it again and say is read as y is a function of x. And of course, the x is the input value, and the y, right, or the f of x, since they're really the same, is the output value. So the x is the input value, and the y, or f of x, is the output value. Now notice, typically we call the function f, but it doesn't have to be. So the function could be named something other than f. So for example, you could have y equals kx. So this still means y is a function of x, but the function is now named k. So I'll say still means y is a function of x. But the function is just has a different name now, right? It's named k instead of f. But the function is now named k. Okay, so here's an example, just sort of in terms of the notation and the interpretation of the notation. Let's say you're told the number of cubic yards of dirt which I'm going to call D, capital D, needed to cover a garden so needed to cover a garden with area A so I'm going to name the area A. And it has units of square feet, so area of A square feet. Is given by D is equal to G of A. So basically what I did, right, is I wrote that D, the number of cubic yards, is a function of A. It's a function of the area, right? The area is my input, and the number of cubic yards of dirt needed is going to be my output. And the function in this case we call G. So D equals G of A. That's how you interpret that. So here's a couple questions based on this information. Let's say you're told a garden with area 5,000 square feet, so feet squared, requires 50 cubic yards of dirt. And we want to express this information in terms of the function G. Okay, so we have to think about this. What is our input? What is our output? Well, remember, A is the input, right? The area is the input, and the output is going to be the number of cubic yards of dirt. So I can write this as, right, we know that it has the form D is equal to G of A. Well, in this case, D is the 50, right? 50 cubic yards is equal to G of the area, which was 5,000. So that's how it would be written. 50 equals G of 5,000. So another question based on that example. How would you explain the meaning of G of 100 equals 1? So what does that mean? So again, think about this, right? The input is the argument of the function G, right? It's what goes into G. That's the 100. And remember, that was the area. The output is the number of cubic yards of dirt that are needed. So I guess, and there's different ways you could write this, but one way of explaining this, you could say, well, this is what this is saying, is that 1 cubic yard of dirt is needed to cover a garden with 100 square feet. All right, and that would be interpreting that equation there, which is basically in function notation. Okay, now it turns out there's many ways that we can represent functions, right? We did it in terms of a set of ordered pairs. We could also represent functions using tables. We can represent functions using equations, which we'll talk about a lot in this class. We can represent functions using graphs, which we'll also talk a lot about in this class. So there's many, many different ways of representing functions. Let me talk a little bit, just briefly, about tables, and we'll do more with tables later on. Okay, so representing functions using tables. Okay, so I'm going to introduce this by asking a question. So which of the following tables represent functions? Okay, so let's say here's my first table, second table, and third table. These are my input values. These are my output values. So input, output. So again, if you want, you can think of this input as X, output as Y, but it doesn't have to be called X and Y. That's typically what we use, but it doesn't have to be called that. Let me fix that. Okay, so the first table, these are my values. Okay, so which of those are functions? First of all, they are all relations, right? Because the table is just another way of writing a set of ordered pairs, right? It's saying the same thing. So all three of them are relations. But which ones are functions? Well, if you look at the first table, remember the quick way of checking of whether something is a function or not is look at the input values. Do they ever repeat? Nope. So this is a function. So I'll say yes. This is a function. Okay, what about the second table? Well, if you look, see how the -2 repeats? So if the input is -2, the output could be 1 or 3. Remember, in order for it to be a function, it can only have one output for each particular input. So this one is definitely not a function. So this is no. And then in the third table, these inputs don't repeat. And it's okay that the outputs are the same, right? Just saying for each input, there's exactly one output, happens to be the same output, but that's okay. So that last table does represent a function. So this is yes again. Okay. Now, what about, and I guess the most common way that we will see functions is written in terms of equations or formulas, right? Equations. So let's talk a little bit about that. Evaluation of functions in algebraic form. So let's say I'm given a function. So let's say it's a function of x, and it's equal to this expression, 2x squared minus x plus 5, right? So actually this is called a quadratic function, right? Because the expression is quadratic. So this is a quadratic function. So given that, let's say we want to find three things. We want to find the function evaluated at -2, so f of -2. We want to find f of, say, a, and then f of x plus h. Okay, so what does that mean? Well, let me go to a new page for this. So I'll write this down again. So I have f of x is equal to 2x squared minus x plus 5. Okay, so first I wanted to evaluate the function at -2. So what that means is, what is the output? What is f of -2? Some people you could even call this y. Or you could call the output y if you want. What is the output, f of -2, if the input is -2? So how do I do this? Well, wherever I have an x in my expression, in my function, I'm going to plug in -2. Now you have to be really careful with the order of operations, right? So I need to do the exponents first, and notice that in this term here, I have -2 squared. The square is acting on the entire -2, so this is really the same as -2 times -2, which is positive 4. So this is 2 times 4 minus a -2. So minus a -2 is plus 2, right? Plus 5. And then 2 times 4 is 8, plus 2, plus 5. So I guess this is going to be 15. So f of -2 is equal to 15. The output is 15. Or again, you could say y equals 15 if you want. Okay, what about f of a? What is the function evaluated at a? Well, all I have to do is, where I have an x, I'm going to replace that with the input, which is a, right? So this is going to be 2a squared minus a plus 5. And that's my answer in this case. 2a squared minus a plus 5. It's in terms of a. And then finally, what about f of x plus h? So same thing. Wherever I have an x, I'm going to stick in x plus h. So I have x plus h squared minus x plus h plus 5. And then we can expand this out, right? So let me do on the side over here. I have, what is x plus h? I need to do this term first, right? Squared. Remember, that's equal to x plus h times itself. So you can FOIL this out. So this is going to be x squared plus xh plus another xh, right? hx, which is the same as xh, plus h squared. So this is really the same as x squared plus 2xh plus h squared. So I have I have 2 times x squared plus 2xh plus h squared minus x plus h plus 5. Now I want to distribute the 2, and you can also think of this negative here as -1, so I can distribute the 2 and think of it as distributing to -1. So this is going to be 2x squared plus 4xh plus 2h squared minus x minus h plus 5. And that's it, right? I can't really simplify any further. There's no other like terms I can combine, so that's my answer. So the output, when the input is x plus h, the output of that function is that entire expression there, 2x squared plus 4xh plus 2h squared minus x minus h plus 5. Okay, let's do some more examples on both tables and functions in equation form. So based on the table below, so here's going to be my table. I'll do a horizontal table. So this is the input x. The output is going to be f of x. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say those are my input values. Let's say the output values are 59, 2, 88, 99, 47, 8, 20, 56, 28, and then 30. Okay, so a couple of questions based on that table. Let's say I want to evaluate f of 8, and then I'll do f of 0 and f of 4. Okay, so to do this, right, remember what f of 8 means. 8 is the input, and then f of 8 would be the output, right? So I go to the table. I go where the input is 8, so that would be right here. Input is 8, and the output is 28. So this must be 28. If I want f of 0, I go to the table. This is 0. I look for the input of 0. What's the output? 59. So this must be 59. And then finally, f of 4, I go to the table where the input is 4. The output is 47. So this must be 47. Okay, and then let's do another question based on this table. Let's say I want to solve f of x equals 30 for x. And then I'll do another one, solve f of x equals 99 for x. Okay, so there's no equation, right? We just have a table, so we have to do this from the table. But when it says f of x equals 30, that means the output is 30, right? So this 30 right here corresponds to the output, which is here. So if I solve f for x, well, what is the particular input that gives me an output of 30? The input is equal to 9, right? X must be 9, because I know that f of 9 gives me 30. And then solve f of x is equal to 99 for x. So I go to, this is saying I want my output to be 99, so I go to 99. Well, what was the corresponding input? It's 3, right? So I know that x must equal 3. Because basically I'm saying that f of 3 gave me the 99, so x must be 3. Okay, how about this? Given the function f of x is equal to x squared minus 3x. Let's say we want to evaluate f of 5. And then later, let's say we want to solve f of x equals 4 for x. Okay, well, the first question is pretty straightforward, right? If I want to find f of 5, this is saying when my input is 5, what is my output? So I go to the function where I have an x, I'm going to plug in a 5. And then I just, expand it out using order of operations correctly. So I would square, right? 5 squared is 25, minus, and then do that multiplication next, 15, and that is equal to 10. So f of 5 is just equal to 10. And if I want to solve f of x equals 4 for x, how do I do that? Well, I have to set f of x, which is this expression, x squared minus 3x. I have to set that equal to 4. And then I can solve it. Well, this is one of our things that we talked about earlier in a previous chapter, right? Solving quadratic equations. So let me bring the 4 to one side. So everything is on one side. Just put everything on the left-hand side. So I need to subtract 4 from both sides. And then the easiest way to solve this is, if it can be done, is by factoring, right? If not, then you have to use quadratic formula or something else. So let's try factoring this. So in this case, I want two things, and multiplied will give me -4, and added will give me -3. So -4 and +1 will work, right? So if I set each of these equal to 0, then in one case I'm going to get x is equal to 4. In the other case, I'm going to get x is equal to -1. So that's my answer, right? So basically what I'm saying is the function evaluated at 4 gives me 4. And we're also saying the function evaluated at -1 gives me 4, right? So those are my two input values that will give me an output of 4. Okay, let's say I give you a relationship and I want you to express it as a function if possible. So let's do an example like that. So express the relationship (3a plus 5b equals 7) as a function And in particular, I want to write a function b is a function of a, if possible. Because it may not be possible. Right? It's definitely a relation, or they call the equation a relationship, where there's a relation between a and b, right? The input and output, but it may not necessarily be a function. So how do I do this? How do I solve this? How do I see whether it actually is a function or not? Well, you solve it for b, and you see if you're going to get just for each input, for each a, you get exactly one b. If that's true, then it is a function. So solve this for b. So I'm solving this equation for b. Well, to do that, I'd have to subtract 3a. So I have 5b is equal to negative 3a plus 7. And then I'd have to divide by 5. So I'm going to get b is equal to, I'll write it as negative 3/5 a plus 7/5. So is this a function? Yes, right? Because for each input a, I'm getting exactly one output value out, right? 1b. For each a, I get exactly 1b. So yes, b is a function of a, and this is what it would look like, right? You could also say this is a function of a. For every input a, there's exactly one output b. Okay, what about, let's do another one. Show you where it can fail. So in this case, let's say we want to express the relationship x squared plus y squared equals 4 as a function. Y is a function of x, if possible. Okay, so what I would do is I would try and solve it for y, right? Try and solve that relationship for y. So again, I would subtract x squared from both sides. So I have y squared equals 4 minus x squared, or you could write it as negative x squared plus 4, doesn't really matter. And then I would need to get y by itself, I need to take the square root, right? But remember, when you do that, you have to account for the possibility that it could be positive or negative. So ultimately, I'm going to get y is equal to plus or minus the square root of negative x squared plus 4. So see how this is not a function? All right, not a function. Because if I put in some particular input, let's say x is 0, then I'm going to get two outputs for y, right? I'm going to get plus the square root of 4, like plus 2 and negative 2. So for each input, it gives me two outputs because I have plus or minus there. So that is not a function. It's a relationship. I can, rearrange it. That's fine, but it's not a function. So I'll say, and the reason is for each input x, there are two output values y. Right? Like for example, if x equals 0, y is equal to positive 2, or y is equal to negative 2. And we can't have two output values for each input value. So it is not a function. All right, what if I give you this graph? So this is my input x. And let's say this is my output, y equals f of x. So 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4. And let's say it looks like, the graph looks like this. Something like that, okay? So, first of all, is this a function? Yes, right? For each input value here, so if I go along my x from 0 to 7, those are all my input values, there's exactly one output value, right? If I go up to the graph, it only intersects the graph in one spot. I'll talk a little bit more about that in a second, how we can check from graphs whether we know they're functions or not. But for each input value, there's exactly one output value. Okay, so based on this graph, let's say I want to find f of 2, f of 3, and an f of 9/2. And then a second question, let's say I want to evaluate f of x is equal to 1 for x. Okay, so let's do the first part first, and I'll do it. I don't want to go on a new page. Let me just do it right here. I'll do it over on the side here. Let's say, so f of 2. So if the input is 2, what is the output? Well, the output, I go up to the graph, the output is going to be 4, right? So the input is 2, the output is 4. What about f of 3? Well, if the input is 3, the output is, I guess it's also 3. So I didn't draw it so great here, but in theory, this should be going right up to that point, which is 3, 3, right? So if the input is 3, the output is 3. What about f of 9/2? Well, 9/2 is 4.5, right? So you can think of this, if you want, you can write it as a decimal, f of 4.5. So if the input is 4.5, what's the output? It's 2. So this is just equal to 2. In fact, if you have any input between 4 and 6, the output is going to be 2 in this case. So this is 2. And then finally, we want to evaluate f of x equals 1 for x, right? So I want to figure out, where is the output equal to 1? Well, the output's equal to 1. So this is, the y is my output, so it's along this. I'll just dash it in here, along that line. So it looks like if the input is 1, the output's 1. If the input is 7, the output's 1. So it looks like in this case, the solution is going to be, let me write it again. So evaluate f of x equals 1 for x. So it looks like the solution is going to be x is equal to 1, right? Because what I'm saying is f of 1 gives me 1, or x is equal to 7, because we know f of 7 gives me 1, right? If the input is a 1 or if the input is a 7, my output is a 1. So basically I picked off these 2 points, here and here. Okay, what about functions that are what's called one-to-one, right? So there's some special functions which have even more restrictions on them, and they're called one-to-one functions. So let me define what that is and how we determine whether a function is one-to-one or not. So determining whether a function is one-to-one. So let me define what a one-to-one function is. A one-to-one function is a function in which each output value corresponds to exactly one input value. So it's a function in which each output value corresponds to exactly one input value. And remember, a function itself, right, is a relation in which each input value corresponds to exactly one output value. So this is just going the other way. So what this means is that a one-to-one function will have no repeated x or y values. Okay, so I'll say there are no repeated x or y values. Remember, if there's no repeated x values, that's what makes it a function. And in addition, if there's no repeated y values, it makes it a one-to-one function. Okay, so here, as an example, let me give you a few tables. So let's say this table is 4, 8, 8, 2, 6, 14. Say the second one is 4, 8, 12, 2, 6, 14, and then 4, 8, 12, 2, 6, 6. Okay, so given those 3 tables, I want to classify them. First of all of them are relations, right? All of them are relations because they're just ordered. You can think of them as a set of ordered pairs. However, which ones represent functions? And then if they do represent a function, do they represent a one-to-one function? So if I look at the first table, right, now my x's, so that first row, are my input values. Well, look what happens here. The 8 repeats, right? So therefore, what's true about that first one? It's a relation, but it's not even a function, right? So this is not a function. All right, look at the second table, the input values. Oh, they're all different, so it's definitely a function. Now let me look at the output values. Well, each output also only corresponds to one input, right? They're all the output values are different. So this is a function. In fact, it's a special function. It's a one-to-one function. So this is a one-to-one function. And then in the third table, let's say all the input values, they're different. So it's definitely a function. But if you look at the output values, they repeat. Therefore, it's not one-to-one. So it's a function, but it's not a one-to-one function. Not one-to-one. Now, in general, to determine whether a graph is a function or not, we use what's called the vertical line test. Tables, you can just look at the input values, and if they don't repeat, it's a function. A graph, it's easy just to use what's called the vertical line test. Let me explain that next. So to determine whether a graph represents a function, we can use the vertical line test. And then further, if you want to determine whether it's one-to-one, then you use what's called the horizontal line test. So I'll say a horizontal line test will determine whether a function is one-to-one. Okay, but first you have to use the vertical line test first, right? Because you don't even need to test the second to see whether it's one-to-one unless it's actually a function. Okay, so let's look at these graphs that I drew, and let's see if they are functions, and then if they're a function, whether they're one-to-one or not. Okay. So again, remember the rule is for it to be a function, it has to pass the vertical line test. What does that mean? It means if you draw a vertical line, it only is going to intersect the function in one place, right? Or the graph in one place if it is a function. So that first one passes the vertical line test. But if I draw a horizontal line, it intersects in more than one place, so it is not a one-to-one function. So I'll say this is a function, but not one-to-one. Okay, what about the circle here? Well, it certainly passes the vertical line test, or it fails the vertical line test, right? So here is intersecting in more than one place. So I don't even need to check to see if it's one-to-one. It's not even a function. So this is not a function. Basically what it's saying is for each input, there's two outputs, right? There's that value and that value. There's two outputs, so it can't be a function. Whereas here with the parabola, for each input, there's exactly one output. All right, what about the line? So it passes the vertical line test, right? So it's a function. And it looks like it also passes the horizontal line test. So it's a function, and it's also one-to-one, right? So it's basically a one-to-one function. 1, 2, 1. Okay, the sine wave. Well, it passes the vertical line test for sure, right? So it's a function, but it doesn't pass the horizontal line test, right? It intersects in several points here, right? More than one. So it's just a function, but not one-to-one. So that's definitely a function. And then finally, this last one here, it passes, so this is like a cubic function that's shifted up. It's definitely a function, right? Because it passes the vertical line test. And it also, in this case, passes the horizontal line test. So this is a one-to-one function. Right, so that's really the quick way of determining whether particular graphs are functions or not. Okay, the next thing I want to do is I want to talk about some functions that are going to appear over and over and over in the course, and we call them the basic toolkit functions. All right, so let me talk about these, and then I'll graph them all using Desmos just because it comes out nicer if I use Desmos. So these are the basic toolkit functions. These are functions that you should be familiar with, right? Because they're going to appear again and again and again throughout the course. And throughout some of your other courses too, like science courses for sure. So the first one is the constant function. So if I have, call it constant. So f of x is equal to c, a constant. For example, because we have to use some particular value, let's say f of x is equal to 3. So if I form a little table here, right, of x and y values, regardless of what my input is, so let's say I'll just use -2, -1, 0, 1, and 2, my output value is always going to be 3. So let me plot that. And it's going to look something like that, right? Where the output values are always going to be a positive 3. So it's just going to be a horizontal line, basically. Okay, the next type of function that comes up all the time is called the identity function. It has the form f of x equals x. So for example, if my inputs are again -2, -1, 0, 1, 2, the outputs are going to be the same, right? -2, -1, 0, 1, 2. So if you plot this, it looks like the following. So that would be the graph of the identity function. So it's basically a straight line, right, that goes to the origin, and it has an angle of 45 degrees. Okay, the next function, the next toolkit function is the absolute value function. So that's f of x equals absolute value of x. So again, if we make a table, let me just use the same values, -2, -1, 0, 1, 2. Then if the input is -2, what's the absolute value of -2? It's positive 2, right? If the input is -1, the absolute value of -1 is 1, so the output would be positive 1. If the input is 0, well, absolute value of 0 is still 0. And then if the input is 1, it's 1. Input is 2, it's 2. So then if we graph that, it looks like this. So if you look at this, right, it kind of looks like the identity function when x is greater than or equal to 0, and it's sort of like negative x, or negative identity function on the other side. So the values, the outputs are always going to be positive. Okay, the next toolkit function is the quadratic function. So that's f of x is equal to x squared. So if I, again, make a table, we'll use the same input values. Then the output values, well, if I square negative 2, so negative 2 times negative 2 is a positive 4, right? If I square negative 1 times negative 1 is a positive 1. 0 squared is 0, 1 squared is just 1, and 2 squared is 4. And if I plot that, it looks like this. So that would be the graph of the quadratic function, and it turns out that graph is a parabola, right? And you can see the values here, right? So 0, 0, 1, 1, 2, 4, and so on, 3, 9. Okay, the next function is a cubic function. So that has the form f of x is equal to x cubed. So again, if I use the same values, negative 2, negative 1, 0, 1, 2. Well, now I need to cube them, right? So negative 2 cubed means negative 2 times negative 2 times negative 2. That's going to be a negative 8. Negative 1 cubed is negative 1 times negative 1, which is a positive 1, times another negative 1, which is negative 1. 0 cubed is just 0. 1 cubed is 1 times 1 times 1. That's 1. And then 2 cubed is 2 times 2, which is 4, times another 2 is 8. And if I plot it, it looks like this. So something like that. And again, you can see here, right, 0 is 0, 1 would be 1, 2 would be A. It's already off the screen here. Negative 1 is negative 1, negative 2 would be negative 8 down here somewhere. Okay, the next toolkit function that you're going to see is a reciprocal function. And that has the form f of x is equal to 1 over x. Or you could also write this as x to negative 1. Okay, they mean exactly the same thing. And for that one, I can't use 0, right? Because then I would be doing 1 divided by 0, which is undefined. So for x values, I'm going to pick, like, say negative 2, negative 1, say negative a half, let's say, something close to 0. Then maybe positive a half, positive 1, and positive 2. So if the input is negative 2, what's the output? Well, 1 over negative 2 is going to be negative 1/2. Right? I'm just plugging in for x. Where I have an x here, I'm going to plug in negative 2. Now I'm going to plug in negative 1. Well, 1 divided by negative 1 is simply negative 1. And then the next one, I have 1 divided by negative 1/2. Well, you can think of this as 1 over 1 divided by negative 1/2. And remember, when you divide fractions, it's the first fraction, top one, times the reciprocal of the bottom. So this is going to be negative 2. So this is just negative 2. Then if I plug in positive 1/2, this is going to be positive 2, positive 1, the output is positive 1, and then positive 2, 1 over 2 is 1/2. And if you plot this, so we can look at some of these inputs, right? If I put in negative 2, so here's my input, negative 2, the output is a negative 1/2. If I put in negative 1, the output is a negative 1. If I put in negative 1/2, the output is negative 2, right? And then on the And of course, I can't put a 0 because it's undefined. And we'll talk about that later. This is what's called a vertical asymptote. I'll talk about that later on in the course. If I go on the other side, if I put in positive a half, my output is 2. 1, my output is 1. 2, my output is a half. Right? So you get this shape. It's called a hyperbola. Okay, the next toolkit function is reciprocal squared. So that's f of x is equal to 1 over x squared. Or you could also write this as x to the negative 2. I'll use the same input values as a reciprocal, so say negative 2, because again, I can't use 0 because I can't divide by 0. I'll get something that's undefined. So I'll just use negative 2, negative 1, negative 1 half, 1 half, 1, 2. So now if I plug in negative 2 into the reciprocal squared function, well, on the denominator I have negative 2 squared, which is 4, so this is going to be 1/4. If I plug in negative 1, I get negative 1 times negative 1, which is 1, and then 1 over 1 is 1. If I plug in negative 1 half, I get positive 1/4. 1 over positive 1/4 is 4, right? And then this is also going to be 4, and then 1, and then 1/4. And so on, right? I'm just doing those 6 points for now, just to get an idea. So if I plot this, it looks... So you can see, basically, all the outputs are always going to be positive, right? And we saw that from the table, too. And if I just pick a couple of these, like, if I put in negative 2 here, my output... it's a very small number. It's negative 1, or sorry, it's positive 1/4, right? So negative 2, positive 1/4. If I do negative 1, my output is a positive 1. If I do negative a half, my output was 4. And same thing on when I have the positive inputs. So positive 1/2 is also 4. Positive 1 is also 1. Positive 2 is also 1/4, and so on. So it looks like that. Okay, and then there's 2 more. So the next one is the square root. So square root function, which is f of x is equal to the square root of x, which I can write as x, remember, to the 1/2. Right? That you can use a rational exponent in this case. So for this one, first of all, because it's a square root, I can't have any inputs that are negative, right? They have to be positive. So I'll choose maybe 0, 1, maybe 4. So if I plug in 0, what's the square root of 0? It's 0. If I plug in 1, what's the square root of 1? It's 1. If I plug in 4, square root of 4 is 2. Maybe use like 9. If I plug in 9, output will be 3, and so on. So if you graph that, it'll look like this. Okay, so again, notice that I can't have any negatives for inputs, right? Because you can't take the square root of a negative number, so everything is positive. And if we just do a few of these, so 0 was 0, 1 was 1, 4 was 2, 9, 3, then you'll find like 16 was 4, and so on. So it looks like, it's sort of like a sideways parabola. Is a square root function. Okay, and then finally, the cube root function is f of x is equal to the cube root of x, which I can write as x to the 1/3. So if I make a table, pick some convenient values that have nice, perfect cube roots, like negative 8, maybe negative 1, 0, 1, 8. So why did I choose negative 8? Because the cube root of negative 8, well, can I think of something times itself gives me negative 8? Yeah, -2, right? Because -2 times -2 times -2 gives me a -8. So cube root of -8 is -2. So -8 is like a perfect cube, is another way of saying it. If I plug in -1, can I think of something where if I multiply it by itself 3 times, I get -1? Yep, -1. 0 is just 0, right? 1 is going to be 1, and 8 is going to be 2, because 2 times 2 times 2 gives me 8. What does this look like? It looks like this. So 0, 0, 1, 1. If I go all the way to 8, this output is 2, right? -1, -1. If I go, I didn't quite get it, but -8 here, it would be -2. Okay, so this is the general shape of the cube root function. So again, those basic toolkit functions are ones that you will see over and over, and we'll talk about them many times throughout the course. So you want to make sure that you're familiar with those particular functions. All right, I want to do one more quick thing, and then that'll be it for this section. It's something called the difference quotient. So let me define what this is. So the difference quotient difference quotient is defined to be this expression. Oh. Let me fix this too, since I can. Quotient. Okay. It's defined to be this expression. So so a function of x plus h minus a function of x divided by x plus h minus x. In fact, that denominator you can simplify. So numerator, I'll just write again, f of x plus h minus f of x. And then if I simplify the denominator, right, the x's cancel, I just get an h there. So this is something actually that comes up in calculus all the time, but it's nice to start looking at this a little bit because it's a nice algebra problem, right? It's really just an algebra problem, even though eventually it'll be used in calculus. And I know many of you won't be taking calculus, but that's okay. We can treat it in this sense as just an algebra problem. So for example, I'll just do one example on this. Let's say we're given f of x is equal to 3x squared plus 4x minus 6, and I want to find the difference quotient. You may see a few of these questions in My Open Math as well, so I think it's good to go over this. Okay, so the first thing I better find f of x plus h, because I'm going to need that, right, when I do this difference quotient. So remember what that means. Go to your function f, and where you have an x, you're going to plug in x plus h. Right? Now, how do we handle, well, we sort of did this one earlier, but let's do it again. I need to square x plus h, right? But remember what that is. This is the same thing as saying x plus h times itself. So I can FOIL this out, and I'm going to get x squared plus xh plus another xh plus h squared. and then I can combine like terms. Xh plus xh is 2xh plus h squared. So then this becomes 3, and then I have x squared plus 2xh plus h squared. So it's a little bit of work, but this is great practice, right? It's an algebra class, so we're going to do a bunch of algebra. All right, now what? Now I need to distribute the 3 and distribute the 4. So I need to multiply the 3, multiply the 4. So I have 3x squared plus 6xh plus 3h squared plus 4 times x is 4x, 4 times h is 4h, minus 6. Okay, so now I can do the numerator at least of the difference quotient, right? Remember, numerator is f of x plus h minus f of x. So I know f of x plus h is the expression I just found, so let me write it out again. And I need to subtract, and you got to be careful here, you're subtracting the entire f of x, so I'll put it in parentheses. Remember that was 3x squared plus 4x minus 6. Right? If I want to remove the parentheses, I need to change the signs, or the other way to think about it is I need to distribute in this -1 here. So the numerator, I'll just write this down one more time. It becomes this. And we're going to find a bunch of things cancel, which is nice. So this becomes minus 3x squared, right? Minus 4x plus 6. Okay, so look what happens. 3x squared minus 3x squared, that's gone. 4x minus 4x, that's gone. And then -6 plus 6, that's gone. So all I have left is 6xh plus 3h squared plus 4h. Okay, so now I can actually form the entire difference quotient. So f of x plus h minus f of x over h. Well, the numerator is what I just found, right? 6xh plus 3h squared plus 4h all over h. And then I can simplify a little bit because I could factor out h from that numerator, right? If I take an h out of the numerator, I'm left with 6x plus 3h plus 4 over h. Now, why did I do that? Because look what happens. I can cancel those h's. So my final answer is going to be 6x plus 3h plus 4. Okay, so that's what we mean by difference quotient. It's really important if you go on at any point to study calculus. For now, we're just treating it as an algebraic problem. Okay, so that's it. And if you guys want to talk more about this in lecture, feel free to ask me questions. We can do more difference quotients. So that's it for that section. The next lecture, I will continue with functions and talk about domain and range. Okay, but that's it for now. Thanks.